No.
Welcome back, everybody, to the online seminar series, Machine Learning Needs Mathematical Optimization. So this is our new season, which is going to run until December. And today we are very happy to have Professor Michela Milano from the University of Bologna. Professor Milano is a full professor of artificial intelligence at the Computer Science and Engineering Department, and she is also the chair of the Interdepartmental Institute of Human-Centered Artificial Intelligence, which is extremely large, 27 departments and more than 400 researchers. Her research activity is around artificial intelligence with a particular focus on decision support and optimization systems. And she has written more than 170 papers which have appeared either in international conference proceedings or in journals, as well as coordinated many European scientific and industrial projects. She is also a past deputy president of the European Association of Artificial Intelligence, past executive councillor of the Association for the Advances of Artificial Intelligence, past member of the executive committee of the Association for Constraint Programming and of the Italian Association of Artificial Intelligence. So we are extremely happy to have you, Michela, knowing that you are a very busy researcher. I would say that you have about 50 minutes for your presentation, and Michela has agreed to take the questions on the go. So if you have a question, please put it on the chat, and yeah, we will warn Michela. Thank you so much, and the floor is yours.
Thank you so much. Thank you for inviting me here. I'm really happy to share with you this topic and this seminar, because this is a topic on which we have worked for kind of 10 years already. So it's a joint work with a number of people that I first of all mentioned. So there are some people from Bologna, but also people from outside, like Thies Gans and Pascal Van Enterich. And we have people from Bologna that are collaborating with me: Michele Lombardi, Alessio Bonfietti, Andrea Bartolini, Luca Benini, Andrea Borghese, and Allegra De Filippo. They're all very active now in this topic. Okay, so the context. I worked in decision support and optimization systems. In general, these systems are systems that have combinatorial problems, so they are very big search spaces to search. We have models that involve variables, constraints, objective function, and in general, what we do when we design a decision support and optimization model, we interact with domain experts, okay? And this is an iterative process. And basically, the thing is that you cannot really assess the accuracy of the model that you have designed. So the thing is that in many domains, we have now a very large amount of data available. So why not extracting from data part of this model? Why not learning from this data part of the model that, and also in this case, we have some known accuracy because we can, at least on the test set, measure how good or how bad is this machine learning model. So really, here now we are trying to put together a model that comes from an expert of the domain and the data that is coming from, a data-driven model, so coming from data. So let me give you a few motivating examples. So suppose that we want to, we have a city where we want to design traffic lights, okay? So either to insert or removing a traffic light over a city, and traffic lights can be connected, like having green wave. There is a budget because every operation has a cost, and you may have many other constraints. And the thing that you want to do is to improve traffic figures, like, for example, waiting times at traffic lights. So we want to solve it. Which is the toughest obstacle? Well, the toughest obstacle here is that, okay, it's easy to describe the cost of the operation, it's easy to put together some constraint, but, understanding the effect of inserting or removing a traffic light on the traffic levels, this is really tough. So you know, we can also have some, you know, some idea through the interaction with experts and come up with some heuristics. But if we have data, then it's really nice to learn it, okay? Also because there is some human behavior involved. The traffic is a complex system. It is based on the decision of single drivers and vehicles, and therefore, I mean, assessing this traffic figure is very difficult. But we can learn it from data, right? So the traffic light placement is a decision. So we want to extract, assess from data, which is the change in the traffic levels, the improvement or the worsening of traffic levels by a machine learning model, okay? So we want to learn the impact on decisions on these observables and basically cast this into the combinatorial optimization model. Second example, this is something that we have done in a previous project that is called ePolicy, and basically we want to achieve a given PV panel adoption, so for improving photovoltaic renewable energy production in a given region. So the region wants to decide to reach a specific amount of PV panels in an energy plan, for example, and we want to and they want to provide incentives to do that, okay? So which incentives to give is very difficult because nobody knows, even policymakers, what is the effect of an incentive on the PV adoption, okay? So how people react to these incentives. One may think that improving the incentives improve the PV adoption, and this is not true because people do not behave rationally, okay? So you might have some constraints that are related to their regional plan, like costs, like number of resources that are available, but the thing that you want to do to learn is to assess the effect of these incentives on the PV adoption. So how people react to these incentives, and this is very difficult to extract from experts because they do not even know. Okay, so they can imagine, but they do not even know, and this also is difficult because it involves human behavior and social dynamics. So we want to learn an effect of a decision that we take on a given observable. So the decision are which incentive I provide, and the observable are the PV adoption levels. So we want to learn this decision through machine learning, and then we have to put this machine learning model into the combinatorial optimization model. Third example, and this is an example that will run through the whole presentation, is an example that concerns thermal-aware workload dispatching. What does it mean? Basically, we have a platform, okay, a heterogeneous platform, like also a system on chip, okay, an hardware platform. And basically, you have a workload, and this platform, sorry, contains computing units, memory, and so on. And basically, you have a workload. So that is an application that you want to run on this platform that can be represented through a graph, and you want to decide the dispatching. So where to allocate this workload, on which cores, for example, how much memory to provide to this workload. And this is easy because you have, for example, you have deadlines, so these tasks should be completed after a given time. They need to have constraints, precedence constraints, and so on. And these are all modeled by the graph of the application, so they are modeled by the domain expert. But the problem is that, you know, in some of these applications, you have some thermal dynamics that you want to control because you don't want the platform to overheat. And therefore, you may have also load balancing constraints, but you have to respect these thermal limits, okay? So the thing that you want to solve it, but the toughest obstacle is to understand which is the effect of a workload allocation on the platform and the thermal dynamics. And this is not impossible to do. I mean, there are some simulators that are models themselves that are based on differential equation and that mimic the thermal dynamics, but they take too much time, okay? So for running a simulation, they take minutes, while you want to have, for example, an answer in few seconds, okay? And therefore, okay, you could use this simulation model, but it's too slow, and therefore you want to learn something more that is faster, and therefore the thing that you do is that you want to understand the decision what is the impact of your decisions, the workload allocation, on some observables, so the core temperatures after a given transition time. And therefore, you want to learn it through machine learning and again cast this into a combinatorial optimization model. So basically, we have a strong combinatorial structure. We have that part of the problem can be described through the interaction with domain expert, but the part of the problem that is not easily described through a manageable declarative model. So the thing that we want to learn is to how to predict the influence on your decision on some observable you are interested in, for example, in constraining this observable, and you have access to problem data, historical, real data, or even simulated one to create a training set. Okay? Okay, so this is the motivating examples. Okay, so if you have question, it's perfectly interrupt me, no problem. So if I can proceed, so how do we learn the relation between decisions and observables? So I decide something and I want to understand the effect on this decision on some indicators that I want to keep an eye on that, okay, because I want to constrain them, I want to optimize them, for example. Okay, let's do our example in thermal management. We have this multi-core system that was an experiment that has already some years. It was an Intel system, single chip cloud computer. It has 48 cores and a fully fledged network on chip in silicon, okay, and 4 memory controllers. So, which is the problem on this platform is that overheating is bad because it can risk to damage the chip. It slows down the tasks on the chip and also the lifetime of the chip. And therefore, we want to reduce. So you have to slow it down when the temperature is starting getting worrying. Then you have to slow everything down or stop some task, and then of course you have poor performances. Okay, so the thing that we want to do is to have a proactive technique that dispatches the workload, keeping an eye on the temperature. Okay. Good. So the thermal behavior of this system is quite complex. Why? Because it depends on a number of things. First, the room temperature. Second, the workload that you allocate on each core, the chip fabric, the position of cores and heat sinks, and also the transfer of heat between cores. Okay. In addition, on the chip, there are some thermal controllers that may enter into operation when the temperature risks to damage the chip, okay? So the thing that we have simulators, okay? We have simulators that we have already used, of course, for mimicking the thermal performance of the platform, but as I told you before, they are too slow for being embedded in an optimization algorithms, okay? So the thing that we want to do is to have a simpler model, okay, that provides an approximation of the phenomenon, the thermal phenomenon, but then we want to understand whether this is basically how can we craft this into the optimization model, okay? So what we want to do is to learn we can monitor the data of the real system or even use the simulator, and we want to create a training set, basically. This is the observation extracted from runs on a real system, okay, with a given allocation. So you have a fixed allocation that you decide, and you produce the temperature, so you observe the temperature after a given delta time, okay, delta t. And you create a training set, okay? You create a training set for each core, okay, with a specific dispatching. So now you create a training set, and you use this training set to train, for example, a neural network, okay, a very simple neural network that takes there is one for each core. You have a neural network for each of these core. You provide to the neural network the dispatching of the core and the neighboring cores, because the temperature of this core depends on the temperature on the other core, because we have a heat transfer between cores, the temperature of the room, and then basically you want to infer whether on core number 3, after a delta time, which is the temperature that you achieve. And of course, you want to limit this temperature, because if the temperature gets too high, then the thermal controller are switched on and everything is slowed down. So these ACPI are average clock per instruction, that basically is a proxy to the dispatch, to the workload that you have allocated on a core. Okay, so that's easy, right? Of course, it's easy. But so now the question is, but how do we insert a neural network that is a machine learning model? And by the way, it's a sub-symbolic machine learning model. How do we cast it into an optimization model? Okay, we have different possibilities, okay? So in principle, you have your combinatorial optimization component that provides a dispatching. You can use a simulator, okay, for example, an evaluator, and then if the temperature after a while is reasonably low, then I can say yes. Otherwise, I can say no to the combinatorial optimization component that should add a cut or a constraint avoiding this solution, and it can propose a new solution, okay? In a way, you know, it's a generate and test process. And this can be very expensive. So instead of the real system, we can use a simulator. Again, it can be very expensive. Oh, there is also a nice proposal that comes from OpQuest, that is a system that has been designed by Miguel Laguna in 2011, to say, well, why don't we insert into this combinatorial optimization component some predictors of the simulation outcome? These predictors basically remove already some solutions that are trivially infeasible from a thermal perspective, right? So we have done, we have substituted, first of all, the simulator that is too slow with a machine learning model. And basically, this goes in the direction of creating these surrogate models that estimate the effect of our decisions on observables. But again, I mean, and this machine learning model is way more efficient than a simulator, because it can take a lot of time during the training, but then using it is very efficient, okay? So the thing that we want to avoid is this generate and test mechanism, okay? So the combinatorial optimization component providing a solution, so a workload dispatching, and the machine learning model providing afterwards, so a posteriori, an evaluation of the solution, okay? We want to avoid the generate and test mechanism. Therefore, this is the core idea of empirical model learning. So we have decided to take this machine learning model and to squeeze it in a way into the combinatorial optimization component. So we have to create an encoding of this machine learning model that is, on one hand, efficient, because the machine learning model needs to be efficient, but in the second place, it should encoded in a language that the combinatorial optimization component understands, okay? And in this case, we do not have a generate and test behavior, but the machine learning model is crafted into the combinatorial optimization component, participating actively in the reduction of the search space during execution. So we want to remove and to prune a priori those parts of the search space that would lead, for example, to a temperature that is too high, that would overheat the chip. And this is done as if it was any other constraint of the combinatorial optimization model that are used for removing a part of the search space that are proved to be infeasible, okay, before exploring them. So this machine learning model can be this embedded machine learning model into the optimization component can be used then to limit, for example, to constrain, for example, the temperature of the core to be below, I don't know, 70 degrees. You can constrain every single temperature of each core. independently, or you can also, you want to minimize the average temperature, the maximum temperature. So you can either use this machine learning model and insert it into an objective function or into a constraint, okay? It can be any relation between decisions and observable. So this is really the core principle of the machine learning model. This is the publication that dates back to 2017, and it's on the Artificial Intelligence Journal from myself, Michele Lombardi, Andrea Bartolini, that basically describes this concept. Okay. But this is most important. These are the two most important slides of the talk. I would think. So what is the difference between using empirical model learning and the traditional use of machine learning models? So machine learning models are trained so that to work forward, okay? So you learn a model that relates the workload dispatching with the core temperature, for example. So you propose a new workload dispatching, and the machine learning model, of course, generalized and tries to predict the core temperature coming out from this workload dispatching, okay? This is the traditional machine learning model. So the nice thing of the empirical model learning is the backward part. So if I constrain the core temperature of the cores to be, for example, less than or equal than 70, as just an example, then this machine learning model becomes a constraint. So we will, in principle, remove all workload dispatching decisions that would lead to inconsistent temperature for our model. Okay, so this really works as a constraint, and working as a constraint, this machine learning model embedded into the optimization model enables to prune the search space and to remove those decisions that are already inconsistent, not in a generate and test methods, but really in a propagation method, as constraints in general do. Okay. Okay, no, so before going down to earth, that in general is not very nice, I would like to know if there are some questions on this first part. Is everything clear? Okay.
Yeah, there is a question, yeah, from Michelle. Jasone, could you give the... Could you give rights to Michelle?
So how can I do?
Yes, okay. So Michelle, would you like to ask your question?
Yes, can you go back to the last two slides and explain one more time? Just we want to pass the other slide. I don't follow this.
So do you want me to explain this again? And is it this slide that you want to learn?
Yes.
Okay. So in general, decision as machine learning models work as follows. Okay, so you have a training set where you have many workload dispatching decisions, and you have in the training set you have the core temperature at the end. Okay, so this is the training set. So you, with a machine learning model, you create a model like a neural network, for example, that generalizes from the training set and devises a relation between workload dispatching and the temperature. Okay, with new workload dispatching, of course, you need to generalize, otherwise the machine learning model is useless. Maybe you can mute your microphone because I hear a lot of noise. Okay. Okay, so and now how do you use the machine learning model? You provide a workload dispatching, and the machine learning model predicts the temperature. Okay, so it's just a forward path. Okay, it's just forward from the workload dispatching to the core temperature. If you want instead to insert this machine learning model into an optimization model, the optimization model has to extract this workload dispatching. Okay, is the decision that you have to take, and basically the core temperature can be can be constrained. Okay, so you don't want to achieve to create any workload dispatching whose core temperature is supposed to, for example, reach 80 degrees, because your top, your maximum temperature that you want to achieve is 70 degrees. Okay, so having constrained the core temperature, you can propagate back this information, and you will tell the optimization model not to choose any workload dispatching that will violate the constraint on the temperature. Okay, is it clear?
Yes.
Okay.
Michela, there is a question in the chat. What is the difference between your approach and a feedback loop within the traditional machine learning method?
So the feedback loop, so in the machine learning method, I mean, the feedback loop is used to train the model. Okay, so we are using a model that is already trained. Okay, so we train it offline. And then we use it inside an optimization model. I will have an example a little bit later, so maybe you can understand a little bit better. Okay.
There are no other questions in the chat, so you can go ahead. Thank you.
May I ask a question? Hello?
Yeah.
Online. I'm wondering about this thermal constraint, the temperature constraint.
Yeah.
How can we play with it in a way of annealing? Namely, change this constraint in a very controlled way and maybe arrive at the optimum faster.
No, wait. So, okay. So that's a good question. But it comes from maybe a misunderstanding. So the optimization model that we are using is not a control model. It is an optimization model that tells you which is the optimal workload dispatching on a specific architecture, and you know as a domain expert that you cannot reach a certain limit of temperature. So this is not a control system. It's an optimization system that decides if a given workload allocation will never exceed the temperature that you decided, you as a domain expert. Okay. So the domain expert provides you the constraint on the core temperature, and the only thing that you have to do is to avoid workload dispatching that will violate this constraint. Okay?
Yeah, that's clear, but still the thermalization or that usage of that analogy calls for considering if you are already dealing with temperature, which is, I understand now, domain expert, okay, or domain knowledge.
Yeah.
It could be possible also to give the annealing sense that is becoming more and more popular in other fields too.
Yeah, but I mean the annealing is a completely different approach. I mean, this might be also an exact model, not a heuristic one. So combinatorial optimization, like examples that I mean, as the example that we do, I mean, is a tree search algorithm or a branch and bound algorithm or whatever you like that provides you the optimal solution given I mean enough time. While I mean all the meta-uniques may provide a good solution.
I understand. Thank you very much, and I'll explore it further. Thank you.
Okay. Okay, so what do you want me to ask other questions?
Yeah, you can go ahead. There are no more questions in the chat. Thank you.
Okay, good. Okay, so now there are a few questions that we have to answer. How do we embed a machine learning model into a combinatorial one? And how do we provide the operational semantic to these models so that they can prune the search space and act in this reverse way accordingly? So we will show two examples very fast. I mean, neural networks and decision trees, and we have mapped these two methods into different optimization techniques. In this talk, I will talk about constraint programming, but we have also, and in the AI journal paper, you can also find mixed integer nonlinear programming, integer linear programming, and SAT modulo theory. Okay, so I mean, artificial neuron, as you know, is I mean, basically a very simple simple mathematical description. So we have an activation function that is the weighted sum of the inputs plus a bias, and then the output is an activation function applied to the neuron activity. Okay, so this is very easy, very simple, and basically is a monotonic, non-decreasing function of the neuron activity. Okay, the activation function. So the thing is that we can cast this into a constraint, okay, because the neural network is a declarative non-linear model. So it can be, for example, embedded into a mixed integer nonlinear logic programming solver directly, okay, we can feed it directly. But basically, if we have a constraint programming model, we have to find an encoding of this neural network that is of course manageable for a constraint programming engine. Okay, and for doing that, we have defined a global constraint that basically takes the input variable, the output variable. So these are our decisions. This is the observable. This is the weights that have been trained during the training part of the neural network, the training phase of the neural network, and the bias. Okay. And therefore, you can propagate the activity. So this is a constraint. So you can propagate the activity backward and forward. So if you have the maximum of the activation function that is updated, so for example, you want to limit the temperature of a core, then you can propagate back and reduce the domain of the variable. Okay, this is for the activation function. For f, just to show the picture, from here to here, from y to a, and from a to x. So we can really propagate back. So this is, for example, a temperature. These are the inputs, and you are going to remove those inputs that will violate y. So every time you change something in the domain of y, and the domain of y is a set of feasible temperature, then you will remove something back into the x, and vice versa. I mean, if something changes in the x, this wants to be propagated on the y. Okay, so this is the traditional behavior of a constraint. Okay, and then using this constraint, you can create a constraint that is an artificial neural network by putting together all these equations that represent the single neurons. Okay, so let me see how it works. How it works at running time, okay, at search time. So you have these tasks, okay, and suppose that we have just 4 cores, I mean, just to simplify the thing, okay. So now here you have to, every time you have an allocation, then you are learning, basically, you are learning from the neural network what will be the temperature of each core. Okay, this is predicted by the 4 neural network, one connected to each core. Okay, you have 1 neural network per core. This is for core 2, this is for core 0, this is for core 3, and this is for core 1. Okay, 0, 1, 2, and 3 are the numbers of core, and these are tasks. Okay, so the color means that they will be very, I mean, computational demanding, and therefore they can be quite pushing from a temperature perspective. So the red one, for example. Okay, so now you start allocating cores, okay, and then you compute the temperature, okay, because you can extract the data. So this clock per instruction that basically is a proxy of this allocation, and you will propagate and understand or predict which will be the temperature of the cores after a given delta time. Okay, so now we start removing. So it works in the following way. If you put some constraint on the final temperature of the cores that you want to reach, then once you have allocated this task on core 2, you know that if you would allocate also this task on core 2, then this constraint would be, for example, for core 2, would be violated, okay? And therefore you remove the allocation for core, from the allocation, possible allocation on core 2, you remove this task, okay? So it acts backward, okay? And therefore, basically, this is the real idea. So we have created a constraint programming model with n tasks, so that are clock per instruction values. Each task is assumed to run indefinitely. We have 48 cores. We have the room temperature. So we have a part of the model that is defined by the domain expert, okay? You try to write some balancing constraints. You want to have a constraint saying that you want that every task goes on one and only one core. You have to average the CPI per core, and you have this neural network constraint that basically is a constraint that takes the room temperature, the average clock per instruction, and tries to predict the temperature of core J, and you have one neural network per core, okay? And you want to minimize, for example, the maximum temperature of the cores, okay? So, and basically this is also published, it has been published in a AAAI paper that was basically trying also to avoid the intervention of the thermal controller on this, in this case, so for keeping the temperature low, okay? So if instead of a neural network we have a decision tree, then constraint programming, this is even easier, because you know, a decision tree is a structure that is done in this way. So you have that in the tree, every level represents an attribute, and basically every node represents a test on an attribute of the training set. And therefore, these while the leaves are the class labels. Okay, so in the leaf we have the class labels. So basically, we can create a decision tree constraint, and you want to create a propagation of this decision tree that is effective and reduces part of the search space. Okay. So indeed, you can have an encoding that is very simple. So basically, you have an implication and you can insert the implication into the constraint programming model. So if the feature A is greater than 20 and the feature C is equal to 0 and the feature B is greater than 20, I don't know, the class is 1, okay? Very simple. The propagation of this implication is not very, very good. So you can define this for all paths of the tree, okay? It is a polynomial size encoding. It's a polynomial time propagation, but it does not enforce any form of generalizer consistent that is very, very important for some constraints, okay? But this encoding is very suitable if you, for example, have a SAT modulo theory problem solver for the combinatorial optimization part. So this is a very nice encoding. We have also another encoding, so we can use a table constraint. The table constraint is a constraint that in general has been that is been defined by Bessières-Rejean in '97, and it is present in basically all constraint programming solvers. Okay. Okay, so we have a technical report where we have created also many other compact encodings of this decision tree using using I mean, many different approaches. Now I don't want to enter into the details. And also we have tried to see the variance, how to how to cast a random forest into a combinatorial optimization model, how to cast regression trees and multi-output trees. Okay. Okay, so some results on this dispatching, workload dispatching examples. Okay, so the thing that every domain expert will tell you, if you don't have this machine learning model available, would be why not trying to have a load balancing on your platform. So this would, in a way, try to keep the temperature quite good. But basically, the thing that I wanted to show you here is that this is the map, or the heat map, that is generated on the course of the Intel SCC platform in different instances, and you can see that by using an expert design model. So the expert design model basically provides, if you don't have any machine learning model on temperature, they will in general use load balancing as a proxy for achieving a reasonable temperature. Okay. But as you see here, these red parts here are some hotspots that are anyway, I mean, that occur when you use an expert design model for the complete optimization model. If you instead choose a machine learning approach, so this empirical model learning approach, then you will see that really the temperature is kept very, very much lower, and the hotspots are definitely I mean, less frequent and less red, I would say, okay, because the temperature is kept in a way that is more balanced, okay? Okay, so this is the solution quality, but I don't want to enter into this. Okay, some discussion part. So I have 10 minutes, so I think that I will conclude quite on time. Okay, so empirical model learning basically enables you to use combinatorial optimization, where in some real complex world, real world problems that. So for which, I mean, understanding the impact of your decisions on some specific indicators and features would be quite difficult or too computationally expensive. And therefore, I mean, that it opens the field of combinatorial optimization to many problems that were kind of a little bit out of reach. So it's, of course, we have worked and presented something related about constraint programming, but you can insert it into any kind of optimization solver or decision-making solver. Constraint programming is very well suited because it's easy to embed an algorithm into a constraint that becomes global constraint, and also it is flexible and modular because the empirical model is just a constraint. Okay, so you can add to this empirical model other constraints that come, for example, from domain experts. And so, of course, for making it work, there should be some things to say. Okay. This is for answering the question. You can always embed a machine learning model into local search or meta heuristics, and the answer is, can constraint programming work better, for example? And the answer is yes, because we have data. So mainly thanks to propagation, we have some results on that. So we have propagation, and basically in local search you cannot exploit this feedback loop that but you try to create a solution and then test it in a way. Okay, so this propagation really removes those assignments that are inconsistent with the machine learning model. So then we need inference methods for this machine learning model. So you have to write basically to find an encoding and find an effective and efficient propagation technique for that specific kind of machine learning models. Okay. So now, you know, the issue now is but how accurate should my machine learning model be for being effective on the combinatorial optimization side? For example, more accurate models are always better than less accurate models, and the answer is no, because more accurate models may result in a slow and weak propagation, and of course this brings to a good poor quality solution, while simpler machine learning models, even if they are less accurate, they have an effective propagation because they are simply simpler to encode, okay? And of course we have the risk that we have apparently good solutions, but maybe they are not really accurate. But there should be an accuracy optimization trade-off we can characterize and you can design some rules for identifying. So on top of this problem, we have in fact worked a few years ago on deep neural networks that are way more sophisticated and more accurate than, for example, shallow networks, but their propagation is really very slow and weak. While for simpler neural network, for sure they are less accurate, but their propagation propagation means the backward loop that removes decisions that are infeasible with a constraint. I mean, this propagation is really way more effective. Then also there is another problem. So suppose that we have a super accurate machine learning model that that is a function that approximates this data. But you know, and this is a very accurate model because the error is very low. But now suppose that your solution is here, the solution of your optimization model. So in this case, suppose that the true value is this one, and the one predicted is here. So here, for example, we have a problem that we have few samples here, and that the solution, the machine learning model is approximating this lack of data here with this point, but it might be very distant from the true value. So the thing is that we are not interested in finding a machine learning model that are accurate in every part of the search space, but we want to learn machine learning models that are very accurate where we are interested in, so in the part of the search space that might reasonably contain the solution that we are interested in, okay? So this is quite difficult because, I mean, you can choose representative observation, you can use concept inherited by black box optimization, surrogate model construction, and adaptive sampling, or also you can overcome this problem with active learning. So you keep on learning actively even during the usage of the model from an optimization perspective. Issue number 4, many machine learning models provide the confidence level. Why don't we take this confidence level into account while optimizing? And instead of devising a deterministic model, you devise a stochastic one, okay? So using empirical model learning in stochastic optimization. This is very important. Also, we have to know that some errors are more important than others. And basically, for example, if you underestimate the temperature, this is way more dangerous than if you overestimate it, okay? Because you think that your core will reach 70 degrees as a top temperature, but since your temperature is underestimated, then the real temperature reach is 80, and this could damage the chip, of course. While if you are overestimating the temperature, the only thing that you may run the risk is that you will not allocate a specific task on that core because of this overheating, and then you will miss some solutions. But in general, it's important to know that there are some errors that are more important than others. There are some extensions that we are working on. One is on hierarchical optimization. Indeed, we have done an industrial application on that, so I cannot really disclose some details, but basically the higher levels of the hierarchy do not know to have all the details of the lower level, so you can learn the behavior of the lower level and cast this into a higher level optimizer. We are working on online and offline optimization, merging machine learning and optimization. And also we have devised a set of applications that are, I think, very interesting. One is on the thermal control in the system on chip, that is the application that I have just mentioned during the presentation. One is on trans-precision computing. Trans-precision computing is computing that you try to reduce the energy by deciding which number of bits to assign to each variable in a program. Of course, you know, you have to learn the error that you will incur in reducing the number of bits. So we have just concluded a European project called OPRECOMP on trans-precision computing. We are using empirical model learning for the hardware dimensioning, for the calibration on participatory algorithms. We have used it for epidemiological models, and also in other groups it has been used for verification and adversarial examples. Okay, so just to conclude, you can find some material on the empirical model learning on this site, emlopt.github.io. You will try find a description, some application example, some resources, like in particular papers, a running survey, the EML-lib embedding techniques, some pre and post processing methods, IO supports for the readers of the most popular machine learning libraries, and also a tutorial with hands-on example that is a very funny tutorial that is on a zombie invasion. Okay, so you can find everything on GitHub on this site. Okay, so I think it's all. I think that, yeah, I was 49 minutes, so quite on time.
Yeah,
so,
thank you so much, Michela. Yeah, you were right on time. Thank you so much.
I'm open to questions.
Yes, and we have time for 2 quick questions, I would say, because we want to finish our half class. So if you have any questions, please raise your hand and we will give you the rights to. So there is a question. So would you like to state the question yourself? So we will.
Yeah, I can see the questions on the chat if you want.
Yes, yes. So
let's keep in touch with you, Michael. Mario, the given example assumed in the runtime of tasks on course. Yeah, so basically, not it was a periodic application. So so it was a periodic application with some deadlines. So we have so they should run indefinitely, because it's always the same application that runs the platform. So thank you for your clarification. I mean, you are right. I mean, I may have said something wrong. Would you use something like model predictive control for dynamic stochastic problem? Okay, so that's a very good question. So model predictive control is somehow related to this empirical model learning, but while model predictive control is meant to take runtime decisions, okay, so as in control systems, as you are trying to learn, I mean, which will be the result of the, so predict the dynamic of your system, and you try to adjust this dynamic. In our case, we are targeting strategic optimization, so that takes decision not at runtime, but for basically strategic scenarios. So, for example, these workload dispatching are in general defined on embedded systems, where you have that there are only a number of applications running there, like, I don't know, in automotive, on appliances, on many embedded systems, and basically you want to optimize really very much on those applications. It's not really a general purpose computer where you have to compile many different programs. Okay, so you want to really optimize and be sure that this chip, for example, or embedded system is running properly. I hope I clarified. I don't know.
Thank you very much, Michela. So if there are no more questions, then we would like to thank you again for coming today and talking about, the use of machine learning for enhancing combinatorial optimization problems. And for the audience, we will see you on Monday next week. Again, same time, same place. Thank you so much.
Thank you. Thank you very much again. Bye-bye.
Thank you very much, Michela. Thank you, everybody. See you.